Hi, and welcome to a short and quick intro to reverting commits in Git and GitHub. So before we deep dive into our conversation today, let's first see how commits are made. In this diagram over here, you'll see a quick overview which kind of depicts a snapshot of the project. If we are to read this diagram, we should start from the far hand side of the screen over here. The blobs that don't have an object stored within the Git basically stores the database of the file system, and then each blob is given an ID that is unique within the repository by generating a SHA-1 hash of that file. In this example right here, we can see 3 different file representations, each one with its own SHA hash. Above each green box, there is a 5-character string that represents the beginning of each of these blobs' SHA hashes. In fact, you only need enough numbers of the characters so that you're referencing a unique blob when you reference to it. On top of that, see how even though each of these green boxes represent a file, there's no file name to it? That basically is the way Git works. So what happens here is that we only reference any blob by a number of characters, which again represent a SHA hash. To go even further, if within a repository you have, or you end up having a colliding 5-digit SHA hash, you end up using more digits from your checksum. And no, at this point you probably won't have to worry. There should be more than enough characters in any checksum to represent a unique blob within the craziest repo you can think of. And by the way, the minimum required number of characters within the Git source control system is 4 characters. That means that for any Git repository, unless there are colliding SHA prefixes or hash prefixes, you're good by only using 4 leading characters of that hash. Now, since there's no file name, you may ask yourself, how does Git even know how to work with the file representation in the file system then? Now, this is where the tree object comes in, this yellow box. This yellow box basically represents the tree that contains all the small changes that were part of any commit. So basically, we will have a tree object which represents each blob of the SHA hash for that blob, and then the file name. So finally, when you have to reference a file to the actual file in the file system, that is happening because of the tree object over here. So finally, on top of that, we have a representation of the commit, which is this white box over here. The commit itself contains a reference to the tree. The reference is created by using yet another hash code, which is calculated, it's this hash over here, which is calculated based on the result of the SHA algorithm applied to the content of the tree itself. On top of that, we have a reference to the author and the reference to the committer as well. We also have the entire comment, which is part of the commit itself. And then obviously at this point you may ask yourself, what is the difference between an author and a committer? Now, the difference between the author and the committer reference is that the author is the person who originally wrote the code, whilst the committer, on the other hand, is assumed to be the person who committed the code on behalf of the original author. This is important in Git because Git allows you to rewrite history and apply patches, if you think, on behalf of another person. So in fact, we'll cover rewriting history in just about a few seconds. So until then, just keep this information in mind. So again, each changed file within any stage, within any single commit, is represented by a blob. This is this green box over here, which is referenced by a SHA hash result. This represents the reference to the file on the file system, and this blob is referenced by the SHA object inside the tree object. Now the tree object is SHA'd as well, as I would say, which gives you yet another tree SHA hash code, which represents the reference to the tree object inside the actual commit. Along with the commit comes the comment and the author and the committer information. The commit's data basically is also SHA'd and eventually gives the SHA result of the commit, which again is a reference to the commit. Is this number over here. Now if you scroll a bit further down on our webpage over here, you see that each commit contains the identifier of its parent commit. Right over here, or right over here, and so on and so forth. Now this represents the reference, this represents a reference to the previous commit. If you carefully look at this tree representation, on the right-hand side, on the left-hand side, you'll immediately realize that there is an exception to the previously mentioned rule, and that is that the commit on the far left-hand side of the diagram doesn't hold the parent reference. That's because this happens to be the first commit. So the first commit, or the initial commit, doesn't hold any parent information, and that's pretty much makes a lot of sense as well. The last commit, on the other hand, the commit on the far right-hand side of the screen, happens to be the last commit. And we know it's the last commit simply because there is no other commit to hold its commit checksum as a reference to it within any parent property. This fact basically gives you the immutability, or simply said, the history fact or the log fact of a Git branch and subsequently of a Git repository. So once you make a commit, none of the commits before it cannot be changed. Otherwise, the commit you made wouldn't be valid anymore. So with this, we finally get to the guidelines of the reverting history scenarios in Git. If you want the too long didn't read version of this, there's a generally safe command which is considered simply safe because it creates a new commit. And this command is the revert command, which creates a new commit whenever you call it. Hence, it's considered safe. So this doesn't delete or remove any other commits such as reset or cherry pick or rebase and so on and so forth. It will just show you just about I will show you in just about a second how you can use either of these commands to revert and then reset your repository altogether. The cherry pick and the rebase commands are topics for another time. For now, we'll just cover revert and reset. So what I want to do at this point is go to this repository over here. Here I have the GitHub Games repository, which is supposed to hold a game. Within this repository, we hold a Tetris game, which is supposed to also leverage GitHub pages. This means that when we visit this URL over here, we should normally see a game of Tetris. But that isn't the case, and the problem for that is the fact that our repository no longer holds the correct code. That means that what we have here is a code that used to work, but no longer works. And we don't exactly know what happened, we simply know that something at some point went wrong, so we have to fix this. So for starters, we'll clone the code. So we copy this thing over, and now I move over to Visual Studio Code. Now in Visual Studio Code, I'm gonna clone the entire repository down. So let's open up the terminal. Let's see what folder we're in. Okay, let's create a directory first, which we'll call Scratch or something like that, because we're starting everything from scratch. Good. We're inside that folder, so now we can clone the entire repository down. We're cloning right now. There we go. So now we can change the directory to our GitHub directory instead. Awesome. So now we're inside our master branch, inside our Git repository. Now that we have the repo cloned locally, we need to first figure out where the issue is and then revert. So our end goal is to basically be able to run the revert command. If we take a look at the revert command, and let's do that right now, git revert, and I'll call out help. Oh, sorry about the typo. Revert. We'll see that the revert command requires a parameter which is our commit. Now again, this is the identifier of the commit, and this comes in as a parameter. So to hold a quick reference of the entire log list, we can call out a different command, which is our git log. And when we use git log, and let me expand this this window over here, we'll actually see whatever happened inside our repository logged. Now, there's an even better looking alternative for the purpose of this scenario demonstration, and that is to use an additional and basically an optional parameter, which is the one line parameter. So we can just say one line, and then we get all the small references and the logs and the history fact basically of our repository within a single line. So we don't get all the extra clutter information such as the author and dates and comments and such on different lines. We only get the checksum prefix or the leading characters, the first 7 leading characters. Remember, only 4 are actually required. That's the minimum, so to say. and the title of the command for that particular commit. Now, when we want to make a revert, at this point, we'll want to figure out which of these commits broke the application. Of course, you could manually do this by manually going through your commits and eventually figure out which commit broke the changes, but that would just take forever, and to be honest, it would be painful. So instead, I will use the bisect command. And this allows you to essentially find where the application broke. Where, in this case, means at which commit did the application start to be inaccessible on the GitHub UI using GitHub Pages. So at the current state of the application, we just know that the application doesn't work. We do know for a fact, though, that the first commit of the application did work. So looking through the logs of the branch, the first commit, this one over here, actually, no, let's take it the other way around. So if we look at the current state of the application, the first commit it had, where the application doesn't work, is the one which appears first in our log. But this is sort of the last one, or the most most recent commit, right? If however we look at the last commit, this happens to be the first actual commit, meaning the most the initial one, the one which has the longest time passing since it has been committed. So now we should tell Git somehow that we want to mark the good and the bad versions of the application based on the commits which were done. So for that, we'll use the bisect command, and we'll say git bisect start. And with that, we are now putting Git in a bisect mode. So next, we'll let Git know that the application doesn't work, but because we don't yet know when the application stopped working, we'll just say had. So basically, we'll say git bisect bad had, and with this, we're basically instructing Git that the application does not work at had. But we'd have to tell Git when was the application working though. So at this point, you can see that the Git is in bisecting mode again, and we're simply starting bisecting the repository. And that sounds like a fun word. The reason for the application not showing up on GitHub URL, again, is for our repository to contain a missing index.html file. GitHub Pages is working based on an index.html file. If that file doesn't exist, it only shows you the README, which is our case. So let's figure out what happened. If you carefully look at the additional information from our repository, the shell outputs, you'll see that the prefix of the checksum is in bisecting mode. So again, let's first tell it that the bisect was good at the initial commit, EA05. And now it will tell me, hey, we're at 1019B whatever in bisecting mode, right? So what we could do at this point is list the index.html file, and that file does exist. So since the file is there, we can now tell Git that this commit is good. So we'll tell it git bisect good. So with that, at this point, something interesting has happened. First, Git has changed the pointer to the next commit, the one starting with F99C, etc. So at this point, our head is no longer heading at the last commit, but then another commit. Which one is this? It's the F99C again, which is this guy over here. So if we do at this point an ls index.html, you see that it tells me that ls cannot access the index.html because no such file directory actually exists, right? So the way this works is that it starts from the end, cuts in the middle, and then tries to narrow it down until it gets the commit which has the problem. So now the pointer basically tells us that we're a commit with the identifier of whatever. If we tell it git bisect bad because this doesn't work, we basically instruct the system that instead of being a good commit, we're saying that no, this doesn't work. And at this point, Git goes further and tries to take another commit, which is the F38CD, which is this one over here. So as I've said, the way this works is that it basically starts from an end, cuts in the middle, and then tries to narrow it down until it gets the commit which has the problem. So a pointer will tell you that you're at the commit with the identifier f3, 8 at this point. So if you do an ls index HTML, we see that the file is there. So we're telling the system, hey, this is a good one. So git bisect good. And now Git realizes, hey, you know what? There's no other commit in between. So that means that at this point, I can figure out exactly which is the commit which has the problem. So now Git identified a commit, which happens to be the first bad commit, because there was literally only a single left commit in between the last good known state, based on the commit we just told Git that it is good, and another commit which was the first bad commit. So we can even see that the comment of the commit in this case was to rename the index.html file to indie.html file, but that's only for demo purposes, of course. So now, which commit to revert is basically a simple answer to tell. But first, we need to get out of the bisecting mode. So we will do that by telling the system git bisect reset. And we have the head reset to master as well. Now, there's a shorter version to do the same thing, and they just feel that this is a must-know at this point. In this particular demo, our check was pretty simple. And since we were only looking for a single file, that is a simple operation. But what if we have a lot of files, or just a large number of commits? Manually going through each and every single commit is extremely time consuming. So there's a more automated way of doing the same command. It's not a shorthand command, but like a shorthand, less time consuming option, I would say. So let's see that in action. So rather than explicitly and manually starting and then going and saying bad, good, good, bad more times, we can just do it in a single line. So for that, we can just say git bisect start head, because this is where the application does not work, so this is bad. And again, this was this one over here, the last commit. And then the good one was EA05, EA05. And again, this puts git in bisecting mode and defines the good and the bad spots right away with a single command. Now, additionally, we can use and will use another command, which is our git bisect run, and we'll basically telling Git to run and evaluate whether a specific command is good or bad based on the existence of this particular file, index.html. So once we click enter, this command automatically evaluates each commit between the bad and the good ones we know are bad or good. And now if you click that, we'll wait for it, and the system automatically tells us that F99C whatever is the first bad commit. Now that we know which commit is bad, let's first get out of the bisecting mode. So again, this is git bisect reset. And at this point, finally, we will just take an additional look at the commit just to make sure that everything is as expected. And here, we basically, if we get another additional look at the commit, we can see the author, the date, and as well the commit message. We also get something called the similarity index, which is this guy over here. And this was created by using a diff between the files when the commit was made. So we can see in this case the similarity index is at 100%. Thus, we know that the file actually wasn't changed, but just renamed when the change was committed. So it's the similarity index. This allows us to see and get an idea of how different the files actually are. So in fact, if the similarity index is too great, Git will know that actually those two files are more or less identical. And this is kind of how it compares the blobs. And remember, the blobs are only a representation of the file, but they don't have a reference to the file name. Hence, also the way for Git to determine that these blobs are similar, in fact the same, without looking at the file name. On top of that, the file isn't completely the same, as it has a different SHA hash, but it does have a 100% similarity index, which again is an indication of how much alike these files are. Now, so at this point, we're just ready to revert our changes. And for that, we just say git revert and tell the system basically which particular, or to specify which particular commit we want to revert. And for doing that, we'll call out the git revert command. And again, this was F99C. And remember, revert is a safe command. And that is because it creates a new commit. But since it creates a new commit, and any commit is required to have a command associated to it, you're required to give in that information as well. So since we didn't specify that automatically, we'll do it in the text editor now, or in VI. So what I'm going to do here is I'll just go with the automatically generated revert rename index.html to index.html, and I'll just say this was wrong or whatever, and then I'll escape this guy and WQ, so I get out of VI. And at this point, if we do a git status, we'll see that there's nothing extra to commit. There's nothing staged, there's nothing in the working tree, so that's good. Now we could also do a git log and use the extra one-line parameter. There we go. And as you can see here, we now have all our original commits plus an additional one which has the revert comment specified earlier. So let's verify, just making sure that index.html is there. And yes, everything seems to be fine, so let's push this to our repo on GitHub again. So git push. Okay, great. Now everything is pushed. Now let's quickly go back to our GitHub repository and using our favorite browser, that is. So if we just refresh, look, this is the unrefreshed web page yet. I'll refresh it right now. And now you can see that indie.html was renamed to index.html. So what I could potentially do is click on the URL, and awesome, now everything works. Well, now we can play Tetris. So even though you're not directly reverting from GitHub, you can do it from the CLI, and that affects the entire repository. And once it is in sync, it also refers the repository on GitHub. Now additionally, the bisect command makes it very easy to determine where the error appears so that you can revert that single commit. Now there's another situation where you potentially want to change the most recent git commit message, or you want to change committed files. And for this scenario, I'm going to use the amend parameter on the git commit command. The git commit amend, or the git commit command with the amend parameter, oh my god, this is such a tongue twister, is a convenient way for you to modify the most recent commit. It lets you combine state changes with previous commits instead of creating an eternally new commit. And you can also it can also be used to simply add the previous commit message without changing its snapshot. But amending doesn't just alter the most recent commit, it replaces it entirely, meaning that the amended commit will be a new entity with its own ref. So to Git, it will look like a brand new commit. So again, if you just go back here, and now at this point we realized, hey, let's do a log, just double checking that we have everything good. We see that, hey, you know what? Our last commit didn't have the right name because we didn't revert index.html to index.html. We did the other way around. So what we could potentially do, we could say that we want to update the command title only of the previous commit, which was created automatically when we called the revert command. And for that, we can just type in something like git commit amend. And -m is the parameter I'm going to use to automatically specify the comment of the commit. And I'm going to say the indie.html name of the file was accidental, reverted the F99C commit. There we go. Click enter. And we're done. So with another git log one line, you'll see that a few things happened. On one hand, we have changed the commit title But on the other hand, you see that from the previous commit, the one created using the revert command, that one disappeared. Why do I say that it disappeared? Because it has different leading set of characters for the SHA checksum. So whilst the commit amend command created a new commit, it is considered a more advanced operation because it involves additional risk. So it kind of removes the other commit from our history. So in other words, we're kind of rewriting history at this point. So let's take a look at this commit one more time. So we're going to do a git show 026c happens to be the leading character, and now we get the similarity and the renaming from, renaming to, and whatever else. But we also get the updated command of that, right? So another frequent scenario which can happen, and does happen quite often with Git, is that when you have done a premature commit and thus may have forgotten to add a file or something like that to your staging, you have to somehow tell the system, hey, you know what, there's an extra file I have to add. Now, for the purpose of this demo, let's first edit, I don't know, the readme.md file. So I'll just open up my editor. I'm going to say readme.md. Okay. Yeah, there's a readme.md file over there. Let's do it like this. Oops. Sorry for all these typos. There we go. We are opening up. We don't want instant markdown right now. We are opening up Node for this. And oh no, this is the incorrect file. We don't have this file here. So let's see what's going on. There we go. Okay. readme.md. Okay, my bad. I've been using here PowerShell specifics command, and sorry about that. So at this point, I want to change the readme.md name, and I'll just say whatever blah blah blah. I'm gonna save the file. So now let's expand the terminal one more time, and if we do a git status at this point, you'll see that we have a file which was not added to stage yet. So let's add it to stage, and we'll just say git add readme.md. And now, if you do a git status one more time, we see that the file was staged, right? So we need an additional commit. Now, in this particular scenario, you simply have to choose between either never altering commits because you want to only play the game very safely, or to go with a team-wide or maybe a company-wide best practice according to which each commit is a working version of your application and code. Here, because say we have prematurely committed the commit, we'll just have to add the file to the last commit with this command, and the command is git commit, just like you normally expect, and we're gonna amend it, but we'll say no edit. Great. So we've seen two, or in fact about 3 ways in which we can revert a history. But now I still want to show you one additional way to revert it. For this scenario, say I want to reset my entire repository for any future demo I'm going to do. So people will have the exact same copy of the repository I had when I started the recording, without the additional recent commits and so on and so forth. They would simply be too confusing. So for this purpose, I'll use the reset command. First, let's make sure that the repository in GitHub is in sync with the local one. So let's just push everything one more time, and I'll do a git push for that. Oh, okay. Let me just push it using the force parameter, and then I'll get back and I'll explain why I'm using force and so on and so forth. So at this point, I'll just clear the entire screen down, and I'll do, as I've said earlier, I'll make it so that we reset the demo to a state that the last commit doesn't exist in the repository. So once again, let's call the git log one-line command. We have here the entire repository which we have changed and so on and so forth. So now what we could potentially do, and let me just show you that we have the exact same thing on GitHub as well. So we have 8 commits at this point. We have this additional commit I just created 9 minutes ago. So what I want to do is reset, right? So for that, I'll call out the git reset hard, and I'll say head circumflex. Now, what happened is that head, rather than being at the last commit, has shifted by one commit. Now, as the CLI instructs, this head being moved to the FA2F commit, which is the previous commit, happens because of my git reset command. This basically instructed and was instructed by the head plus the circumflex sign, which in Git language means the last commit, or up one commit. Another option would be to use the tilde sign, which is this one. So I could do head tilde 2 or head tilde 3 and so on and so forth. And this basically, using the tilde sign and specifying a number of commits to revert, is telling Git to revert this many number of commits. Also, we have specified the hard parameter. This makes the reset command reset the index and the working tree so that any changes to tracked files in the working tree since the specified commit will be discarded. An alternative is the soft parameter, which does not touch the index or the working tree at all, but resets the head to commit only, just like all modes do. This leaves any changed files in the file system locally, and as a git status command would put it, these would just be changes to be committed. Now let's look at the log now. So if you do a git log, one line, you see that the last commit no longer appears because our head is heading somewhere else. So what you potentially want to do at this point, because you've removed, so to say, one commit, is to push your command. But when we push, we get an error. And this error happens because our centralized repository, the repository which we have cloned locally, is one commit further, right? By using reset, we're basically taking our head behind. We're moving back in history. But now, the system knows that we are a commit behind. So what we could potentially do to reset the demo is to force the push by using the force parameter. So I'm going to do a git push force, and this will instruct the centralized repository which we have cloned that we want to force this version of the repository which we have locally, because this is the good one where we have reset our code. So now if we go back to GitHub, remember, we had this 1CE, 1B, 5D commit. We refresh, poof, the commit is done. So there you have it. Now we have reset the demo. So in conclusion, there are many ways to revert history, and throughout this small experiment we have played around with many of them, but not all though. So stay tuned for another part with some more advanced commands which impact your repository's history.